Have you ever wondered if you could create electricity just by squeezing something? It sounds like something out of a fantasy novel, but it's actually a real phenomenon that happens in the world around us. Imagine holding a simple crystal in your hand and, with just a bit of pressure, generating a tiny spark of energy. That's not magic, it's science, and it's called piezoelectricity. This effect is one of nature's most fascinating tricks, where a simple squeeze can unlock hidden power within certain materials. The word piezo comes from Greek, meaning to press or to squeeze. So piezoelectricity literally translates to squeeze electricity. It's a perfect name for this surprising effect. Certain materials, especially some crystals like quartz and tourmaline, can generate voltage when you put them under stress. These crystals are special because of the way their atoms are arranged, making them sensitive to pressure. Push, bend, or hit them, and you'll trigger a flow of electricity. Even a gentle tap can be enough to set off this effect. They make electricity. It's almost as if the crystal is storing up energy, just waiting for you to release it with a squeeze. This isn't rare or futuristic. It's all around us, hiding in everyday objects. You might be surprised to learn how common piezoelectricity is in our daily lives. When you squeeze these crystals, you're shifting their internal structure just enough to separate positive and negative charges, creating a voltage. This tiny movement inside the crystal is what makes the magic happen. It's like waking up a tiny battery with a squeeze. The energy is small, but it's real, and it can be harnessed in clever ways. The effect is small, but incredibly useful. Think of gas grill lighters, which create a spark to ignite your barbecue, or the precise ticking of a wristwatch, powered by a sliver of quartz. It's a direct conversion of physical effort into electrical energy, a bridge between the mechanical and electrical worlds. Every time you press, you're turning force into power. Engineers have harnessed this property in countless devices, from microphones and sensors to medical ultrasound machines and even musical greeting cards. But how does pushing on a solid crystal create a spark? The answer lies at the atomic level, where the tiniest shifts can have big effects. It's all about how the atoms are arranged and how they shift when pressed. The unique structure of these crystals allows them to separate charges when deformed. We're about to dive into the heart of a crystal to see this atomic dance in action. Get ready to see how a simple squeeze can set off a chain reaction at the tiniest scale. Get ready to discover the electrifying science of piezoelectricity, and see how a simple squeeze can power the world in ways you never imagined. Let's look at a familiar example, the barbecue lighter. When you press the trigger, you hear a click and see a spark. No batteries required. The secret is a tiny piezoelectric crystal inside. Squeezing the trigger compresses a spring, which releases a hammer to strike the crystal. That sharp impact generates thousands of volts in an instant. The voltage travels to the tip, where it jumps a small air gap as a spark. That spark ignites the gas, giving you fire. Your muscle energy becomes a spark through a chain. Squeeze, spring, hammer, crystal, voltage, spark. It's a perfect self-contained system powered by the piezoelectric effect. Every click is a real-life demonstration of turning force into electricity. To understand how this works, let's shrink down to the microscopic level and explore quartz, a classic piezoelectric material that has fascinated scientists for decades. Quartz is made of silicon and oxygen atoms arranged in a repeating hexagonal crystal lattice, forming a beautiful and intricate structure. The bonds between these atoms are polar. Oxygen hogs electrons, becoming slightly negative, while silicon is slightly positive. This polarity is crucial for the piezoelectric effect. This creates a grid of tiny positive and negative poles, like a 3D array of microscopic magnets, each contributing to the overall effect. For the piezoelectric effect to work, the crystal must be cut along a specific axis, just like cutting wood with the grain. This ensures the alignment of the poles. The orientation is crucial. Pressure must be applied in the right direction to generate an electric charge. In its resting state, the charges inside the crystal are perfectly balanced, canceling each other out. This balance is delicate and easily disrupted. The centers of positive and negative charge overlap, so there's no voltage. The crystal remains neutral and inactive. The crystal is neutral, just waiting for a push, a force to disturb its equilibrium. But when you apply force, everything changes. The balance is disrupted, and the crystal responds. The atomic arrangement is the key to unlocking the crystal's hidden power. Each atom plays a role in this transformation. Let's see what happens when we squeeze it. The pressure causes a shift in the atomic structure, generating an electric charge that can be harnessed for various applications. Imagine squeezing the crystal along its special axis. The pressure deforms the lattice, shifting atoms in a coordinated way. Positive silicon atoms move one way, negative oxygen atoms the other. Now, the centers of positive and negative charge are separated. This creates a voltage. One side of the crystal becomes positive, the other, negative. You've made a tiny battery powered by your squeeze. The more you squeeze, the higher the voltage. Stretch it, and the voltage reverses. This predictable, proportional response makes piezoelectric materials perfect for sensitive electronics. It's a simple, elegant cause and effect at the atomic scale. The effect is reliable and repeatable. That's why these materials are so valuable in technology. Squeeze and you get electricity, every time. Why aren't all materials piezoelectric? It's a fascinating question, especially when you consider how many different types of crystals and minerals exist in nature. Yet, only a handful possess this remarkable property. What makes some materials special, while others remain ordinary? There are two strict rules that determine whether a material can be piezoelectric or not. These rules are like a secret code that only a few crystals can crack. First, the crystal must have polar bonds, meaning its atoms have different charges, creating tiny electrical dipoles within the structure. This is essential for generating an electric response. For example, diamond is made entirely of carbon atoms sharing electrons evenly. Because the charge is perfectly balanced, there are no polar bonds, and therefore, diamond cannot be piezoelectric, no matter how beautiful or strong it is. Second, the crystal must lack point symmetry, a center of inversion. If a crystal has this symmetry, any electrical effect produced on one side is cancelled out by the opposite side. If you can draw a line through the center and find identical atoms mirrored on both sides, the piezoelectric effect disappears. The symmetry causes the charges to neutralize each other. In quartz, this symmetry is missing, so when you squeeze it, the charges can shift in one direction, creating a measurable voltage. This is what makes quartz so valuable in electronics and sensors. Only materials with both polar bonds and no point symmetry can generate voltage from pressure. Both conditions must be met. One without the other simply won't work. That's why piezoelectricity is rare and special. Out of thousands of known crystals, only a select few meet these strict requirements. The atomic arrangement must be just right, an intricate dance of atoms and bonds, perfectly aligned to allow this phenomenon to occur. These two rules define the exclusive club of piezoelectric materials. Only those with the right internal structure and chemistry are allowed in. Only a select few make the cut, making piezoelectric materials both scientifically intriguing and technologically invaluable. The piezoelectric effect works both ways. Squeeze a crystal, get voltage, that's the direct effect, but apply a voltage and the crystal changes shape. This is the inverse effect. The electric field pushes and pulls the atoms, making the crystal expand or contract. The movement is tiny but precise. This is how piezoelectric buzzers and speakers work. Apply a rapidly changing voltage, and the crystal vibrates, creating sound. Greeting cards that play music use this trick. The same disc can act as a microphone. Vibrations generate voltage, or as a speaker, voltage creates vibrations. This dual ability makes piezoelectric materials perfect for sensors and actuators. They're used in everything from medical ultrasound to sonar. Electricity and motion, perfectly linked. The quartz watch is a marvel of piezoelectric engineering. Inside, a tiny quartz crystal shaped like a tuning fork is powered by a battery. The circuit applies voltage, making the crystal bend. Inverse effect. As it bends, it generates a feedback voltage, direct effect, creating a stable oscillation. The crystal vibrates at exactly 32,768 times per second, a power of 2. Easy for circuits to count. The watch divides these vibrations down to 1 tick per second. The result, incredible accuracy, unaffected by most temperature or motion changes. The crystal's stability keeps you on time, all thanks to the piezoelectric effect, ticking away on your wrist. It's a tiny, reliable pendulum for the digital age. From BBQ lighters to quartz watches, piezoelectricity powers countless innovations. It's the science of turning pressure into electricity, and electricity into motion. This property, found only in specially arranged crystals, bridges the mechanical and electrical worlds. Piezoelectric materials are used in ultrasound, car sensors, musical instruments, and precision motors. Their versatility is staggering, and their role in technology is growing. Imagine roads that power streetlights or clothes that charge your phone. These are real research areas. The potential to harvest energy from everyday motion is immense. Next time you click a lighter or check your watch, remember the tiny crystals at work. Piezoelectricity shows how understanding atoms leads to powerful innovations. Sometimes, a little pressure really can create something electrifying.